Hey everybody, welcome back. Alright, so I've been told that my videos are a bit on the boring side, so I'm going to try to make more jokes, but I've also been told that my jokes aren't funny, so got to work with what I got though. Okay, so you might have noticed that I'm wearing all black today, so I'm not actually just a floating head and arms, but anyway, you might be wondering, why am I wearing all black today? Well, um, it's because I'm a morning person. Yes, morning person. All right. Anyway, silly jokes aside, today we are going to be starting on Chapter 8, which is hypothesis testing for our elementary statistics course. All right, and then in this lecture, we're primarily going to be doing 8.1, but we're also going to be covering a lot of 8.2. So it is going to be quite a long lecture, and it's possible that I'll split it up into two parts, but I haven't decided that yet. But obviously, if the video says part 1, then you'll know that I'll make another lecture. But I'm hoping to get them all done in this video. And this video, hypothesis testing, is sort of the culmination of everything we've learned in the course. And we're going to be primarily focusing on hypothesis testing for proportion. And remember that a proportion is represented by the letter P. Okay? So a formal hypothesis test is the goal here. And the concepts in this section are general. So even though we're focusing on proportions in this video, a lot of the stuff we're learning here can also be used for means, standard deviations, or variances. Okay, so as they're pointing out here, these are good general ways of doing hypothesis tests, but the focus of this video is just going to be proportions. In other words, the population proportion P. Okay, so first of all, what is a hypothesis? So if we were in a science class, in some classes, hypothesis might mean more of a guess, but instead of rather a guess, in statistics what it means is it's a claim or a statement about a property of a population. Okay? So if a hypothesis is a claim or statement, then a hypothesis test, which is what we're learning how to do in this section, is just a procedure for testing whether that claim is supported or not supported by the evidence that we have from our data values. Okay? And again, we're focusing on the population proportion P. Okay, but the stuff we're learning here can also be used for mu or sigma. All right, so what does a claim look like? Well, it's generally going to be an inequality. Not always, but for our class, it's going to be inequalities. So you're either going to have a less than, a greater than, or a not equal. So consider the claim from the chapter problem in our book that most internet users utilize two-factor authentication to protect their online data. Using P to denote the proportion of internet users who utilize two-factor authentication, the claim that most internet users, or the majority of internet users, is equivalent to the claim that the proportion is greater than half. Okay, so I know that's kind of strange, but when they say most, they just mean P is greater than 0.5. And the reason that should make sense is 0.5 is the same as 50%. So if P is greater than 50%, we're just barely the majority, right? But it's enough to be considered a majority for a hypothesis test. Okay, so the expression P is greater than 0.5 is a symbolic form of the original claim. And actually, for our class, we're primarily going to be focusing on claims that either use greater than, less than, or not equal. So our claim is actually going to be the same as our alternate hypothesis, or alternative hypothesis. Okay, so that's on this slide here. So in this problem, we just said that the claim was P is greater than 0.5, okay? And the claim is the same as the alternative hypothesis, or some people just say alternate hypothesis. And the alternative hypothesis, denoted by H1 or HA, the A can either be capitalized or lowercase. In our class, that's going to be the same as the claim. Okay, so here the claim is going to be, the way we would write it is, I like to just write H1, but you can also write HA. It means the same thing. So our claim that we got on the previous, well, not the previous slide, but 2 slides back here, the claim is the same as the alternative hypothesis, and it was P is greater than 0.5. So H1 or HA is going to be P is greater than 0.5. Okay, and if you do a harder statistics course, you may have situations where your claim isn't actually the alternative hypothesis. But for our class, that's how it's going to be. So the reason they call it the alternative hypothesis primarily has to do with the fact that the parameter has a value that somehow differs from what's called the null hypothesis. Okay? So for the methods of this chapter, the symbolic form of the alternative hypothesis must use one of these 3 symbols: less than, greater than, or not equals. Okay? So the way I teach it is, the first thing you do is you write out your claim, which here was P is greater than 0.5. And then whatever your claim is going to be the same as your alternative hypothesis, H1 or HA. Okay? So then what's this null hypothesis that they're talking about here? Well, the way you get the null hypothesis is you just simply replace the inequality symbol with an equals. So that's very straightforward to do, and that gives us the null hypothesis. So the null hypothesis, denoted by H0, or people like to say H0. Okay, so H0 or H0 is a statement that the value of a population parameter, such as the proportion, which we're focusing on in this video, the mean or the standard deviation or the variance, is equal to some claim value. So literally, for your null hypothesis, you just go ahead and you write H0 or H0, and then you write a colon, just like we did with the claim, which was our alternative hypothesis. And then we simply replace this symbol with an equals. So we still have P on the left side, and we still have 0.5 on the right side. The only thing here is we replace it with an equals. And some books teach this a different way than our book, but I'm trying to follow what our book does. So in our book, it's actually quite straightforward to write out the null hypothesis, because you just write out the alternative hypothesis first, which is your claim, and then you replace that symbol with an equals every time, and that gives you your null hypothesis, or H0. Okay? Now the idea with a hypothesis test is you're testing to see if the evidence that you have either supports your claim or if there isn't enough evidence to support your claim. So you either support your claim or you don't support your claim, which means you default to the null hypothesis. So we're going to learn more about that in a bit. But let me switch to the PC view so we can erase this. All right, so how do you make your null hypothesis and your alternative hypothesis? We just talked about this, so I'm going to go through this pretty quickly. Step 1 is identify the claim to be tested and express it, as we did. So first you write out your claim, And then the book makes this seem more complicated than it needs to be. They say give the symbolic form that must be true when the original claim is false. I say the easier way to do that is to just replace your inequality symbol with an equal, the way we did. Okay, and then the alternative hypothesis, H1, is always the one that contains either less than, greater than, or not equal, whereas the null hypothesis, H naught, always involves an equal symbol. So you just replace these symbols with equals, and then you're good. Okay. So we kind of already wrote out the claim, and I already worked out this problem. So real quickly, returning to our example, step 1 was to identify the claim. That was P is greater than 0.5. Step 2 in our book is they say you sort of do the complement of the original statement. So instead of P is greater than 0.5, in our book, they replace it with P is less than or equal to 0.5. However, just remember that you're always going to be writing an equals for your null hypothesis. So this step 2 that they have in the book isn't that useful in our class. Step 3 is, once again, they kind of make this seem complicated, but if you want to read through, this is straight out of our book. Basically, all they're saying here in our book is that the alternate hypothesis is our claim, which is less than, greater than, or not equal. And then the null hypothesis just replaces this symbol with an equals. Okay, so next thing we need to talk about, there's a lot of stuff in this section, so I'm going to try to move it along here. The next thing we need to talk about is the significance level. So the significance level, alpha, is the same as 1 minus our confidence level that we were learning in chapter 7, the previous chapter, when we talked about confidence intervals. Okay, so the significance level, alpha, this letter here is alpha, and it looks like, it almost looks like an A, but it's a Greek letter, alpha. For our hypothesis test is the probability value uses the cutoff for determining when the sample evidence constitutes significant evidence against the null hypothesis. Okay, that's very long-winded. This is taken straight out of our book. So basically, the significance level is the probability of mistakenly rejecting the null hypothesis when it is true. Okay, but I like to simplify it. Our book is kind of wordy about all this. So the significance level alpha is equal to the probability of rejecting H naught when it's actually true. Okay, so the thing is, you can figure out your significance level in the problem based on the information they give you. So sometimes they'll just tell you the significance level. In fact, on most of your homework problems, if not all of them, they will just tell you what your significance level is. But I just wanted to point out that you can always calculate it, and it's the same as the alpha that we talked about in section 7.1 in the previous chapter when we were talking about critical values, okay? And then the common choices for alpha, which is the significance level, are 0.05, 0.01, and 0.10. But on the vast majority of the problems we'll be doing, we'll be using 0.05. And that's the same thing as 1 minus our confidence level. But like I said, in our homework quizzes and exam, they're pretty much just going to tell you what alpha is. They'll say, use a significance level of 0.05, which means alpha equals 0.05. Okay? So that's not too incredibly difficult. So we just need to return to our problem. Okay, so returning to our example, actually, let me just go back to this slide back here. So we already did steps 1, 2, and 3. Step 4 in our book is identifying alpha. So alpha isn't written in the original problem here. because they were lazy, I guess, when they were writing the book, and they didn't want to confuse people as well. But if we skip ahead later in the slides, at some point they will tell us what significance level to use, although they're being a little bit dense here. Okay, so the significance level on this problem, I wish our book would be more clear about this. The significance level on this problem is alpha equals 0.05. So actually, way later in the slides, they tell us what alpha is. So just remember, alpha is the same as the significance level. Okay, so in this problem, we know that they were supposed to tell us earlier on, but alpha equals 0.05. Okay, so let's kind of step back and work through the rest of this example, and we'll kind of introduce new concepts as we go along. But for example, we're going to be using alpha equals 0.05. Okay, so after you've identified alpha, which is given to you, step 5, indicated in our book, is to identify the test statistic that is relevant to the test and determine its sampling distribution, such as normal, t, or chi-squared. Now, at the time I'm making this video, we're not going to be getting to chi-squared. So we're going to be focusing on normal in this video, which is with z-scores. Okay, but just for the sake of being thorough, I'll talk about the other distributions, even though we won't get to more than one of them on this video. Okay, so on this page, we're going to see a table which is very thorough, but at least at the time I'm making this video, we're just focusing on the first row. Okay, so in this video, we're focusing on a parameter of a proportion p, and for a proportion p, we can use the normal distribution as an approximation for the binomial distribution, so we're going to be using z-scores. Okay, these requirements here are useful if you're actually doing statistics in the real world, but for our homework quizzes and exam, these requirements will already be satisfied. So the requirements are NP is greater than or equal to 5, and NQ is greater than or equal to 5. Okay, and then for a proportion P, this formula here gives us our test statistic. So in this video, we're only going to be looking at this first row, and we're only going to be using this test statistic for P. Okay, so Z equals P hat minus P all over the square root of PQ over N. Just keep in mind that P hat is the same as your sample proportion, whereas P actually refers to the population proportion P that P is equal to in your null hypothesis. So we'll return to that. But if you're trying to do hypothesis tests for a mean mu, then you would be using one of these two rows. And then if you're trying to do a hypothesis test for a standard deviation sigma or variance sigma squared, you would actually be in this last row. But for us, we're going to be focusing on just this first row. Okay. So like I said, the requirements are met in all of our homework problems, but here they have it worked out. N equals 926 in the two-factor authentication problem, P equals 0.5, and Q equals 0.5. So remember that P is the P that we got in our null hypothesis. So going back to that slide, remember we said our null hypothesis was the one with the equals, so that's how we got P equals 0.5. And then with that information, we also know that Q equals 0.5 because if you probably remember this, Q equals 1 minus P. So here, because P is 0.5, Q is 1 minus 0.5, which equals 0.5. Okay, but the requirements are going to be satisfied, so we don't have to worry about it. I just left it in there in case you're curious about the requirements and you have to do this with statistics in the real world. Okay, so because the requirements are satisfied, let's go ahead and move on to the next thing, which is doing this test statistic. This is a formula you have to use, but it's not too bad. We've seen a lot of formulas like this before. So z equals p hat minus p over the square root of pq over n. Here we already said q was 0.5 and p was also 0.5. We got p from the null hypothesis. Okay, and then let's do the test statistic. So actually let me switch to a view where we can do all this. So z equals p hat minus p over the square root of pq over n. In this problem, we said n was 926. Okay. So let's actually switch to the camera. All right, so our formula for the test statistic z is p hat minus p all over the square root of pq over n. Ooh, I wrote that too high. I'm so sorry. Let me just write that a little bit lower. So z equals p hat, there we go, minus p all over the square root of pq over n. So the whole reason I wrote down that p was 0.5 from the null hypothesis, q we got from 1 minus p, so 1 minus 0.5 is 0.5, and then n was 926. So the last thing we need here is just p hat. So how do we figure out p hat? Well, that'll be usually just given to you. Okay, if they don't give it to you, you can also do it as x over n, where x is the number of successes. Okay, but if we return to PC view here, so they said that p hat is 0.52 in this problem right here. Okay, so that will generally be given to you like this in your homework and quizzes. So because p hat is 0.52, let me just write that down here. Okay, so this is the main math that we have to do here. Calculator is obviously going to be helpful, but let's just write down the numbers first. So p hat, they said, was 0.52. Okay, so we have 0.52 minus p, which we said was 0.5, all over the square root of pq over n. So here, p is 0.5 and q is also 0.5. So that's going to be 0.5 times 0.5 over n, which was 926. Okay, so how do we plug all this into our calculator? Well, like I've said before, it kind of depends on what calculator you're using. But I'm going to go ahead and grab mine. So for most calculators here, you would either want to do the numerator and then the square root separately first and then plug in the numbers. Or if you wanted to type it in all at once, you have to be careful because you would need to put, if you're typing it in all at once, you do need to put parentheses around the numerator. So you would put parentheses around this, and then you would press the division symbol on your calculator or the fraction symbol, and then you would type in your denominator. So, like I said, there's a number of ways of typing that in, and it depends on the calculator. But some people have come to my office hours and asked about how to use individual calculators, and of course you always have YouTube. So you can just type in your particular calculator, and then you could just type in how to, on YouTube, you can look up how to work with your individual calculator if you're having any trouble. And don't forget, I have office hours every week. And then I usually have tutoring hours in person, at least at the time I'm making this video. So, all right, anyway, on my calculator, what I would do is I would just type in, let me show you how I would type it in. So I would do parentheses 0.52 minus 0.5 end parentheses. Okay. And then in order to do this fraction here, I would go ahead and press the division button on my calculator. And then I'm going to do the square root button on my calculator. And on my particular calculator, when I press the square root button, it automatically sort of puts everything after that in the square root. But if your calculator doesn't do that, you might also need to put parentheses around the denominator when you're typing it in. Okay, but for mine, it kind of does that automatically. Okay, and then I would type in 0.52, sorry, not 0.52, 0.5 times 0.5. So I would just do 0.5 times 0.5. Okay, and then I would divide by 926. Okay, so after we do all of that, so divide by 926, then we would just press enter or equals. But obviously there's all types of calculators out there. So your steps might not be the same as ours, but when in doubt, you can put in some extra parentheses. And a lot of calculators also have a fraction button, so you might be able to just type it in without parentheses if you're using fractions. But anyway, after I press enter or equals on my calculator, I should get 1.2172. Okay, now this thing that we just calculated, this is called the test statistic. So remember, we're doing a test of a claim. So the test statistic is what we're calculating now. This is important, and it's actually a z-score. So this number that we got here is a z-score. And because it's a z-score, if we're using table A2, which is what we usually use for areas of z-scores, we are going to need to round this to 2 decimal places. So instead of writing z equals 1.2172, I'm going to go ahead and round here. So it actually rounds to z equals 1.22. Okay, so the test statistic that we got here was z equals 1.22. All right, so that took a little while to explain, but I like to do math on the board now and then, even though it's kind of time consuming. So let's go and return to these slides and see what they got while I erase all this. So what we just did caused what is called a rounding error. Okay. So this is kind of an interesting situation. So looking at the slides, they initially said that p hat was 0.52. However, they had rounded that. So I actually need to redo this real quick. So I used 0.52, but on the slides, I kind of purposely did that. Sorry, let me go back to this. So the 0.52 that I plugged in for p hat was actually already rounded. So what we just did gave us a test statistic, but it isn't very close to the correct one. So the problem was they had already rounded 0.52 on the slides. And so the moral of the story is we were actually supposed to plug in more digits for 0.52. So what we just did in this video, or what I just did, was actually called a rounding error. And it was caused by this 0.52, which they had already rounded. And we used that, and that actually messed up our answer. So the number we should have gotten was actually closer to 1.25. So let's look at the PC while I erase all this. So this is all included in our slides, which are lecture notes. So note, don't round anything until the end. If we plug in p hat, this was actually the original fraction that they started with, but they had rounded it, and I just fell into the trap of a rounding error. So you just saw me do that. So what we were supposed to do is we're actually supposed to plug in p hat equals 0.520518355. So if you do all the steps I just did, but you plug in that more precise version of p hat that hasn't really been rounded, where they've written out all the digits, the formula will look something like this. Of course, on your calculator, you may need to put parentheses around the numerator and the denominator, as I already mentioned. But this is an important thing to learn about, because rounding errors are very common, and it's something that we need to avoid, especially if we're doing statistics in the real world. Okay. So basically, we weren't supposed to round until the end. Because 0.52 was already rounded, that would give us the incorrect value of z equals 1.22, which is what we got. But it actually should be z equals 1.25. Okay. So the moral of the story is don't walk into the trap that I just walked into. So don't round anything until the very end. Okay. Until you actually just get to a single number on your calculator. Make sure you include all the digits, even though it's tedious to type in all those digits. All right, cool. So that is the test statistic. So these things are pretty long, but we're moving at an okay pace. So hopefully my video will not be much longer than an hour, but we'll see. All right, so the next thing we're going to talk about is critical regions or rejection regions. Now, if you've taken another professor before, or if you've taken statistics in high school, or you've watched other videos, you may have learned about the critical region. In other words, a critical value marks the boundary of a critical region. And what a critical region does is it's the area corresponding to all values of the test statistic that cause us to reject the null hypothesis. Now, there's nothing wrong with using critical regions, and you can do the whole problem that way, and it's totally fine. However, the book that I'm using for these videos focuses more on p-values, which is another approach. So we'll be using the p-value method. However, I'm still going to talk about the critical value or the critical region method, because it helps us to understand what type of test we have. So there are three types of tests: two-tailed tests, left-tailed tests, and right-tailed tests. So there's a lot of information on this slide, but only some of it's particularly helpful. Really, all they're saying here is for a two-tailed test, the way you know it's two-tailed is if your alternative hypothesis uses the not equal symbol. So the reason the not equal symbol gives you two tails is because not equals in your alternative hypothesis, so you're going to have H1 is going to involve the not equals symbol. Not equals means either less than or greater than. That's what it means. Okay, because if it's not equal to a number, then that means it has to be either smaller than that number or bigger than that number. So the less than and the greater than gives you these two tails. So roughly speaking, that's what's going on. So that's why it's called two-tailed. Left-tailed test would be where you just have a tail on the left side. And this one is probably easier to understand. So if you remember from, if you've taken algebra courses or if you've learned about inequalities, less than goes to the left. So whenever your alternative hypothesis involves a less than, well, less than goes to the left. So a left-tailed test involves less than for your alternative hypothesis. Okay, and then the last case is right-tailed test. So remember that greater than goes to the right. So it should make sense using the same or similar reasoning that if our alternative hypothesis involves the symbol greater than goes to the right. And looking at these pictures, the reason this one is called left-tailed is our critical region is this green area on the left side. So left-tailed refers to this region on the left side, whereas greater than gives us a right-tailed test. So the region is this tail on the right side. And then for a two-tailed test, obviously we have a tail on both sides. So this one is the less than, that one's the greater than. So that's why it's called two-tailed. Okay? But it all comes down to H1. So you can tell what type of test you're using just based on whether H1 involves a not equal, a less than, or a greater than. Okay? All right. So let's continue this. So you can use critical regions if you've learned them before, but like I said, our book focuses more on p-values, so that's the way I'm going to teach it. There are two different ways of doing the same thing. Some people would argue that critical values and the critical regions are easier. Other people argue that p-values are easier and p-values are more useful because once you have a p-value, then you actually have a number to work with instead of making a picture and all that. But anyway, we're going to focus on the p-value method. So with the p-value method of testing hypotheses, we still need to decide whether it's a left-tailed, right-tailed, or two-tailed test. But once we know that, we're able to calculate what's called the p-value using our test statistic. Okay? So the p-value is the probability of getting a value of the test statistic that is at least as extreme as the test statistic obtained from the sample data, assuming the null hypothesis is true. Well, this is just our book being wordy again, but to kind of say that in plainer terms, with the p-value, we're just going to end up calculating it, and it's either going to be sort of the area to the left, the area to the right, or the two-tailed area. And we can look that up in either table A2 or using technology, because it's a z-score that we got for our test statistic. Okay, and this stuff about assuming the null hypothesis is true, we're going to worry about that a bit later. For now, let's just calculate the p-value. So going back to our example, our ongoing example in this lecture, using the data from the previous problem, the test statistic that we got without the rounding error, obviously the way I wrote it on the board was fine, and I plugged it in my calculator, but we had a rounding error because they had actually rounded p hat. But the one without the rounding error is z equals 1.25. Okay. So they say that it's a normal distribution with an area of 0.1056 to its right. So the way you look that up is using table A2, because our z-score was 1.25, what we're really trying to determine is the probability that z is greater than 1.25. So the 1.25 is the same as our test statistic, and the reason it's greater than is, remember that our original alternative hypothesis in this example was p is greater than 0.5. So going back to that, remember H1 involved p is greater than 0.5. So because that involves a greater than, this greater than here just gave us this greater than up here. Okay? And like we were just saying, greater than corresponds to a right-tailed test. Okay? But a right-tailed test, in order to look that up, you just use table A2. So it's the same as the area to the right. Okay, so from table A2, you do 1 minus the area in table A2. Oops, wrote too far over. So it's 1 minus the area in table A2. Okay, so the row in table A2 would be 1.2 and the column would be 0.05. And then we do 1 minus that area. And then after we do 1 minus that area, that actually gives us the p-value. So for a right-tailed test, that's the same as the area to the right. A left-tailed test is the area to the left. And a two-tailed test, which we won't be seeing a lot of, but for a two-tailed test, rather than being the area in the middle, it's actually going to be twice the area at either extreme. So we'll see that in a second. But if you look up the area in table A2, which I recommend doing right now, if you want to pause the video, look it up, then you're going to do 1 minus that area. Okay? And if you do 1 minus that area, it gives you an area of 0.1056. Okay. So the thing is, if you're using technology, as we've talked about before, the p-value or the area that we look up will be slightly different. So here the p-value would be 0.1059 if you're using a computer or a calculator, but 0.1056 is what you get if you use 1 minus the area in table A2. Okay. And just to make sure that you got the area in table A2 correctly, the area in table A2 that you should have gotten would be 0.8944. Okay, so this right here, that when you look it up in the table, you should get an area of 0.8944 from 1.2 is the row and 0.05 for the column. All right. So the name of this thing that we just found here is called the p-value. So we're primarily going to be focusing on left-tailed tests. For a left-tailed test, that's the area to the left. And right-tailed tests. For a right-tailed test, that's the area to the right. But for a two-tailed test, we'll also briefly talk about how to do that. So let me return to the lecture notes. So if you're finding a p-value, we do have this whole flowchart here that's in our book. Now, some people find this helpful, other people find it a little bit confusing, but I left it in the slides in case you want to look at it. So if we're looking at this right now, if I zoom in a little bit so we can actually read it, basically, when we're calculating a p-value, which is what we just did for a right-tailed test, there's really 3 cases. So left-tailed, which just means the p-value is the area to the left of the test statistic. So for that one, you would just literally look up the area in table A2. And remember that less than goes to the left. And then the case that we just saw was actually a right-tailed test, because greater than goes to the right. And because greater than goes to the right, that means we're right-tailed. So the p-value was the area that we just calculated. That was the area to the right of the test statistic. But the thing is, if we're using table A2, then the area to the right, as we've talked about many times in earlier lectures in this course, the area to the right is 1 minus the area in table A2. Okay, and then the kind of more obscure case, let me switch to the overlay so we can see me a little better. The more obscure case for your type of test is this case in the middle. So for whatever reason, this is actually the flow chart in our book. For whatever reason, they didn't write two-tailed here, but they meant to write two-tailed here in the middle. Okay, so left-tailed is this branch, right-tailed is that branch. Two-tailed is the hardest case, but basically all you're going to do is if the test statistic z is to the left of center, in other words, if your z-score for your test statistic is negative, then the p-value is going to be twice the area in table A2. Okay? So you just do 2 times the area in table A2 if your z-score is negative. Okay, so when they say, is the test statistic to the right or left of center? If it's to the left, in other words, if your z-score is negative, then you just do 2 times the area in A2. Okay, so 2 times the area in table A2. Okay, and then the hardest case is if your test statistic z is positive and it's a two-tailed test. So in that case, the p-value is twice the area to the right of the test statistic. I don't think we ever actually see this case in our homework and quizzes, but I'm just going to talk about it in case you ever have to do it in the real world. So all we have to do here is, because it's 2 times the area to the right, remember that the area to the right is 1 minus the area in table A2. So it's going to be 2 times the area to the right, which is 2 times parentheses 1 minus the area in table A2. Okay? All right, and then let's return to the flow chart while I erase this stuff. But anyway, this left side, so this left branch here, these are all for a two-tailed test. This middle branch here is for a two-tailed test. If your z-score is negative, you use 2 times the area in table A2. If your z-score is positive, or it's to the right of center, then you do 2 times 1 minus the area in table A2. Another way of thinking of that is it's just twice the area beyond the test statistic. That might be easier for some people and confusing for others, but I'm just going to mention that. But let's go ahead and return to the flow chart if we can switch views here while I erase this. Okay, so what do these pictures look like here? Well, for a two-tailed test, when they say a negative z-score, they mean it's going to look like this. So your z-score is going to be to the left of center, so it's going to be a negative z-score. And in this case, the p-value is 2 times the area to the left, which is 2 times the area in table A2. Whereas over here, if your z-score is positive, the p-value is 2 times your area to the right. So if you're using table A2, obviously the area to the right is 1 minus the area in table A2, but then we have to multiply that times 2 because it's a two-tailed test. So long story short, left-tailed tests and right-tailed tests are pretty straightforward, but two-tailed tests are a little bit trickier. But just remember that for a two-tailed test, because it has 2 tails, you're either going to be using the area to the left or the area to the right, but you'll have to multiply the result that you get from that times 2 because it's two-tailed. So that middle branch and all of this corresponds to two-tailed. Okay, so let me zoom back out here. Whew. That was not the view I meant to be in. All right, so good stuff here. So let's see what's next. So we just talked about p-values in quite a bit of detail. We're still under 1 hour, so I have hopes of finishing this video around an hour, but let's see how I do because we have a little bit more stuff to talk about. So one other thing I wanted to talk about is don't confuse the p-value with the lowercase p. That's very common. Remember, lowercase p refers to the population proportion, whereas the p-value is the area that we just talked about. So there were really the three cases. It's either left-tailed, which is the area to the left, right-tailed, which is the area to the right, so 1 minus the area in A2, and then two-tailed, which is going to either be 2 times the area in A2 if you have a negative z-score, or 2 times 1 minus the area in A2 if you have a positive z-score. Okay, or in our book, they say the p-value is the probability of a test statistic at least as extreme as the one found from the sample data, assuming that the null hypothesis is true. But I just think of it as an area that we look up. That's usually an easier way to think of it. P is the population proportion that shows up in our null hypothesis and our alternative hypothesis. Don't confuse that with the p-value. Okay, and also don't confuse either of those with p hat, which is your sample proportion. And remember, if they don't give you p hat in the problem, just recall we've seen p hat before, and the formula for p hat equals x over n. Back in my video from chapter 5, or videos from chapter 5, we talked about the binomial distribution. P hat is the sample proportion, so it's the number of successes x over the number of trials n. Okay. All right, so believe it or not, there are more steps to a hypothesis test. So once you've calculated your p-value, which we have done for this problem, you have to make a decision to either reject your null hypothesis, H naught, or fail to reject your null hypothesis. So fail to reject confuses people, the wording of it, but think of fail to reject as a double negative. So it's sort of like the two negatives cancel in a way. So basically, if you reject your null hypothesis, that means the data is supporting the other hypothesis, so your alternative hypothesis. But if you don't reject H naught, then you don't have enough data to support your claim. Okay, or in our book, they call this the decision criteria for the p-value method. This is the approach that we're going to focus on because that's the approach they focus on in our book. So you compare your p-value to alpha. Remember, alpha is the level of significance, and the p-value is the area that we just looked up, which is going to be generally looked up in table A2. Alpha is the level of significance. So if the p-value is less than or equal to alpha, you reject H naught. We'll talk more about what that means later. But if the p-value is greater than alpha, you fail to reject H naught. So the p-value we got on this problem was a p-value of 0.1056 because it was a right-tailed test, so 1 minus the 0.8944 gave us our p-value. So all you have to do for these problems when you're in this step 7, is you have to compare the p-value on the left to your level of significance alpha on the right. So in this problem, our p-value was actually 0.1056. So you write your p-value first, and then you write alpha second. So alpha in this problem, I had to skip way ahead in the slides because they didn't include it, but alpha, they told us, is the level of significance. and that happened to be 0.05 here. So in our example, which is the chapter problem from this book, just write your p-value first and alpha second, and then decide whether this should have a greater than or a less than or equal. And if the less than or equal confuses you, just think of it as a less than. So obviously, if we compare the p-value to alpha here, we have 0.1056 is greater than 0.05. Right, so greater than, so that means the p-value is greater than alpha. Okay? So that's actually the confusing case, which is good. So if our p-value had been less than or equal to alpha, we would reject the null hypothesis, which would mean we were supporting the claim. Or in the book, they say, if the p is low, the null must go, which is just kind of a saying they use in the book. However, we're in this case here. If the p-value is greater than alpha, which we did have on this particular example, you fail to reject H naught. So a lot of people find the wording fail to reject H naught to be challenging. So let me talk about the way I usually explain it, so for people to understand it. So if you reject H naught versus fail to reject H naught, it's one or the other. So remember that our original claim here in this problem was H1. Actually, let me write that a little bit lower here. Okay, so our original claim in this problem that we did at the beginning of this video was the same as H1, and that was the same as P is greater than 0.5. Our claim is the same as the alternative hypothesis. And then the null hypothesis was H naught or H0. We replace this greater than symbol with an equals. Okay? So it can get more complicated, but for our class, the claim is always going to be the same as the alternative hypothesis. So either we have evidence to support this claim, or we don't have enough evidence to support the claim, which means we support the null hypothesis. Now, you can't really say support the null hypothesis, because the null hypothesis is sort of like a default case that we go back to. That's why they use this confusing wording of fail to reject. But because in this example, we got a p-value is greater than alpha, that told us that we fail to reject our null hypothesis, or H0, okay? But like I said, the way most people can understand fail to reject is as a double negative. So fail to reject means you do not reject H naught. So which of these two is supported? Well, if we do not reject H naught, that means that we aren't supporting H1. Okay. And I purposely included this example because this is the confusing case. So if you reject H naught, then there is enough evidence to support your claim. So that's all you say. But if you fail to reject H naught, a double negative sort of cancels out, and that means that we don't have evidence to support the claim. We do not reject the original null hypothesis. So here, you can't really say support the null hypothesis, so you say fail to reject the null hypothesis. But one thing that's helpful is you either have to have evidence that supports your claim or does not support your claim. So it either has to be, it supports your claim, which is your alternative hypothesis. In that case, you would reject H naught. Or the case that we're in right now, if you fail to reject H naught, that means you don't have enough evidence to support your claim, so you're just stuck with the null hypothesis. And another way of thinking about it is like sort of like a criminal trial. So people are innocent until proven guilty. So the null hypothesis is by default, there's not enough evidence to support the claim. So by default, we're stuck with the null hypothesis. So that's why they use fail to reject H naught, because you're not really supporting the null hypothesis, but you don't have enough evidence to support your claim, so you can't reject your null hypothesis. In other words, you're not guilty by default. So it's kind of the same idea as that. Okay. Anyway, hopefully that long explanation helped. If not, just try to, don't forget you have on your homework, you have the option to click the button that says view an example or help me solve this. So it actually has some detailed steps for each type of homework problem. So that can help with all this, because I know this is a lot of information, especially because, you know, this is close to the end of our course. This is really close to the end of the semester, or if this is a summer class, we might be close to the end of that session. All right, so there's a bit more to talk about here. So we are going to go over an hour. We actually were already over an hour, but that's okay. So just remember in your homework, quizzes, and exam, write your p-value first, alpha second, and then it's either going to be you reject H naught, so you support your alternative hypothesis, or you don't reject H naught, which means there's not enough evidence to support your alternative hypothesis. And the alternative hypothesis, again, for our class, is always going to be the claim. Okay, so here they did all the same steps we just did. So fail to reject H naught. And then here's an interesting explanation. It may or may not be helpful to you, but the p-value is the probability of getting a sample result at least as extreme as the one obtained. So if the p-value is high, which is greater than alpha, the sample statistic is not considered significantly low or significantly high, which means we can't really reject the null hypothesis. So that's like the not guilty case, not innocent by default. Okay. So in other words, there's not enough evidence to support the claim. So the book says to restate the decision using simple and non-technical terms. So without using technical terms not understood by most people, state a final conclusion that people can actually understand. Okay, so continuing with our example, because I know I just erased it, but we already talked about this. Because we are not supporting the claim, right? I actually circled the null hypothesis, so there wasn't enough evidence to support the claim. So because there wasn't enough evidence to support the claim, we did not reject H naught, which means that in our conclusion, we just say that. Okay, so there is not sufficient evidence to support the claim. Okay, and then here they're just stating the same claim that they started with. So it doesn't need to be any more complicated than that. You can just leave it that way. And then, of course, if you have to interpret it, though, it can be a little bit more confusing. They do have a flow chart for interpreting. For most of your homework, you're probably not actually going to use this, but I left it here in case you ever have to like write a paper for another class and you want to refer to this video for help. But so when you're wording the final conclusion, there's only one case that leads to wording indicating support for the claim. So you're either going to reject H naught, which means you're supporting the claim, or you fail to reject H naught, which means you can't support the claim. There's not enough evidence to support the claim. Okay. So it's more detailed than what's actually in our course, but this flowchart has all of the cases. The only cases you're going to have to worry about for our course are all the cases on the left side. So in other words, let me zoom in here to show you what I'm talking about. So if you happen to do a problem that's not in our homework, quizzes, or exam, then you might have to use this right branch over here. But that's kind of an unusual case that we're not covering. So for our course, we're going to be focusing on the left side of this. Okay, so basically, the original claim is going to be our alternative hypothesis, which means it's not going to contain equality, at least not in this section. So it's either going to be less than, greater than, or not equal. So then we're just going to be focusing on this part of the flowchart. So these two cases here. So let me actually circle that, or at least do something here. This part right here. Okay, so looking at this right here. So at the end, we have to decide whether we reject H0, which would be a yes, or fail to reject H0, which would be a no. And so we're really only, for our class, it's an elementary statistics class, we're just focusing on these two cases. So either there is not sufficient evidence to support the claim. That would be where we fail to reject H0. That's the case that we just saw. Or if we reject H0, there is sufficient evidence to support the claim. So like I said, for our course, this is the only part that we're going to have to focus on. But just in case you have to do statistics for another course or out in the real world, you can also refer to this right branch. So this would be an unusual case, but if your original claim actually contained equality, they don't really cover that in our book, in this section anyway. But if your original claim contained equality, in other words, it was the null hypothesis in a way, but it's actually the claim, then you would refer to one of these two cases. But just focus on these for our class. And then the rest here, if your original claim contained equality, then you would have to use one of these two branches based on whether you fail to reject H0 or reject H0. Okay. All right, so hopefully that clears that up a little bit. So let me zoom back out, and then we'll return to this slide and go to the next slide. Okay. So I know the wording of fail to reject is confusing, and it seems like they should just say accept. So that's why I included this slide in my presentation today. So the problem with saying accept is it's misleading. So you can't accept the null hypothesis, all right? And so just in the interest of science, that's why we have to keep it kind of deliberately vague by saying fail to reject. Okay, so we fail to reject the null hypothesis instead of saying we accept the null hypothesis, because the term accept is misleading. It implies incorrectly that the null hypothesis has been proved or is somehow being supported. Okay, you can't prove, this is just one statistical test. You're not going to have a census. So in your statistical test, you have a sample. Okay, so because you're not doing a census, you can't prove something. So the only way to prove it would be if you have a census of the whole population. But then it's not really statistics. Then you would just your p hat would equal p. Okay. But for actually doing statistics, you can't prove the null hypothesis. So you have to use this deliberately vague phrase that has a double negative. So you have to use the phrase fail to reject. Says more correctly that the available evidence isn't strong enough to warrant rejection. So you do not reject the null hypothesis. So it's almost like you support the null hypothesis, but even saying support is a bit much. But again, on this slide, we kind of talked about that. So rather than thinking about supporting the null hypothesis, just think about whether you support the claim, which in our class is going to be H1. So that would be this right here. Or you don't support the claim. So if you fail to reject H0, you can't reject that. So that means you're stuck with H0, so you can't support the claim. You don't have enough evidence to support the claim. And as they point out in our book here on this slide, final conclusions can include as many as 3 negative terms. Just try to, if you have to write a statistics paper in the real world, just try to take out as much of that as possible. So, for example, instead of saying there is not sufficient evidence to warrant rejection of the claim of no difference between 0.5 and the population proportion, a better way to say it that people could understand would be, until stronger evidence is obtained, continue to assume that the population proportion is equal to 0.5. Or at least that's the argument they make in our book. Okay, so this is sort of just saying, well, we failed to reject H0. Okay. All right, so that is it for this video. We did go over an hour, but we got it all done in one video. So it says 1 hour and 11 minutes. So thank you for watching as always, and I will see you in my next video. All right, bye.